Hey, before we get into the chemistry today, I want to offer a quick apology if anyone tried to come to my office hours today. I had something this morning that took a lot longer, and I wasn't able to let you know about that. So I apologize for that, and I'll try in the future to make sure I notify you in the rare occasions when I'm not around during scheduled office hours. The other thing that's I'm sure on a lot of your minds is the results from the exam that we're currently taking. The last of you are either taking it now or a little bit later. And if you want to see your results from that and review them, they should be open up about 8 p.m. tonight when everybody's finished taking them. You would just go in through the Blackboard grade book like you do for homework assignments if you want to review those, and you click on the score, and it'll take you to the questions. And just like we do for homework, it'll likely just have the correct answer and the answer that you chose, not all of them. I am willing to go over, or encouraging you if you want to come see me and go over exams with me in my office hours sometimes. So if you have questions about which problems you didn't get right or didn't understand, or you just want to talk about tips for improving your score in the next exam, I'd be happy to do that in the future. So once you guys can see those results, we can arrange things like that if you're interested. All right, we have a couple of our typical pre-health announcements to open up with. So Alpha Epsilon Delta has a meeting this week, Thursday, tomorrow, and another combination of Greek letters, Alpha Eta Alpha, has some physician assistant and Kaplan info also, I believe, tomorrow. So you have to choose between those two if you're interested. But again, all these societies advertise and want you guys to come out if you're interested. All right, so what we're going to cover today is the last part. Okay, we're starting now for real. So we're going to cover the last part of Chapter 4. We had to kind of go fast through Chapter 4. That's sort of how the syllabus was arranged, but we just have one major topic left to cover, which is molecular orbital theory. And so we've talked about, we started Chapter 4 talking about the shapes of molecules, and then last time we introduced sort of the first bonding theory that we are going to discuss, which is valence bond theory, and that's the idea that you have these localized atomic orbitals or hybrid orbitals in many cases, and those individual orbitals overlap to form bonds. So the key distinction with that bond theory is that you still have individual orbitals on each atom. So your central atom often has a bunch of hybrid orbitals that are associated with it. Your outer atoms have some combination of atomic and hybrid orbitals potentially as well. And it's those individual orbitals on each atom that overlap to form bonds. Now, what we're going to talk about today is a new theory called molecular orbital theory, or abbreviated as MO theory. And this one is a delocalized model. So instead of having just local orbitals that overlap, we're actually going to make new orbitals that are delocalized over the entire molecule. They no longer belong to one atom or another atom. They actually belong to the entire molecule and are delocalized over that entire molecule or a large part of it. So why do we need another bonding theory? Why can't we just be happy with valence bond theory and move on with our lives? So the reason for this is that there are some things that valence bond theory does not correctly predict, and it even gets as simple as the Lewis structure of some of the properties of oxygen, O2. So based on what we know now, we could easily draw a Lewis structure for O2. We would start with oxygen and oxygen, and to make sure we complete the octet and use the correct number of electrons, it would be a double bond. We add 2 pairs on each oxygen, and we call it a day. So a relatively simple Lewis structure that we should know how to do very easily now. And then based on what we talked about last time, we would say that each of these oxygen atoms could be thought of as being sp2 hybridized. They have 3 electron groups, 2 lone pairs, and 1 bond, and then that this bond that forms would be a combination of sigma and pi, 1 sigma bond, 1 pi bond to make that double bond. So that's kind of where we stopped last time. Now, if you look at this Lewis structure and you think about the arrangement of the electrons in this thing, if we wanted to predict how many unpaired electrons are there in O2, what would we guess from this structure? Does it look like there's any unpaired electrons? We're not talking about non-bonding, we're talking about unpaired. So, okay, it would be 0. I heard someone say it, 0. Because when we do this valence bond approach, and we're using Lewis structures as kind of our backdrop for that, we sort of assume that all electrons pair up with each other. So we get these non-bonding pairs of electrons, and unless we had a situation where there was an odd number, we would never have a situation where we would predict that electrons remain unpaired in a molecule like this. Now, because of that, something we haven't talked about yet, but we are going to touch on a little bit more today, is magnetic properties. So when you decide how many unpaired or paired electrons something has, we talked about it in the context of individual atoms and say we're going to do it for some kinds of molecules. If you assume that you have 0 unpaired electrons, the magnetism is what's called diamagnetic. And so if you predict something is diamagnetic, what would happen is if it interacts with a magnetic field, it would be weakly repelled by that field. So at a basic level, there's 2 types of magnetism, 2 types of magnetic properties. There's diamagnetic, and this is when you have 0 unpaired electrons. So all the electrons are paired. And if you have 0 unpaired electrons, it's diamagnetic, and it interacts weakly with the magnetic field but is repelled if anything. Whereas the other type is called paramagnetic, and paramagnetic is when you have unpaired electrons, 1 or more unpaired electrons, and in that case you expect the substance to be attracted to a magnetic field. So let's see what happens with oxygen. So I have not my own but somebody else's YouTube video to show here. And so what this experiment is going to do is, as you can see right where my pointer is, there's 2 magnets that are really close to each other. And then these 2 people, presumably chemistry instructors somewhere, I'm not sure where, they have samples of liquid oxygen and liquid nitrogen. So we're talking especially about oxygen in this case. So the first experiment he's going to do is he's going to take liquid oxygen, really cold obviously, but still O2, and he's going to dump it through these magnets that are close to each other. Let's see what happens. So again, the prediction is that if oxygen was diamagnetic, if all the electrons were paired, it would go right through. It would be repelled by the magnetic field. All right.
Between the poles of the magnet.
All right, but we see in this case it's actually stuck to the magnets. Now it eventually goes away because it boils off into the atmosphere, but the liquid oxygen stays right between the 2 poles of the magnet, the 2 magnets that are pointed towards each other. All right, and then again, when it goes away, it's just because it's boiling and becoming a gas again, not because it's being repelled or anything by the magnetic field. All right, and I think eventually they're going to put nitrogen through there as well. So that's oxygen. Oxygen clearly is attracted to the magnetic field, which is not what we would predict. So she prematurely ended the video and said, "Thanks for watching." And he said, "Well, wait a minute. What about nitrogen?" I'm narrating for you guys because I can only hear the sound. All right, so he puts oxygen through again, it sticks, and then when you put nitrogen through, as you see, it goes right through. So nitrogen would be diamagnetic, meaning it goes right through the magnetic field. Oxygen, which is what he has, sticks between the 2 magnets. Okay? So that's what we observe for oxygen, is that it's attracted to the magnetic field. And we conclude then that O2 is paramagnetic, and what that means is that it has unpaired electrons. 1 or more unpaired electrons. Electrons. Okay? So again, we would never predict that from drawing a Lewis structure or considering the valence bond theory with sigma and pi bonds and hybrid orbitals and all that stuff. So this clearly shows us that we need a more sophisticated, more accurate bonding theory. Now the reality is this bonding theory is more complicated mathematically and even conceptually in a lot of ways. So we're only going to talk about it for simple diatomic molecules like O2. We're not going to go into anything more complex than that. But we do want to introduce sort of the foundations of it and how we use it to make certain predictions about properties of these simple molecules. Okay, so let's sort of in an abstract level talk about what are the tenets or the rules that we have for this molecular orbital theory. Okay? Okay, so what we have is we still have mixing of atomic orbitals. We saw that for valence bond theory. We often mix atomic orbitals, make hybrid orbitals. The difference here is we're mixing atomic orbitals from 2 different atoms, or 2 or more different atoms. That's kind of the big difference. So these atomic wave functions, remember these are mathematical functions at their origin. They're nothing more than that. From 2 different atoms, or if you're going more complex than that, 2 or more different atoms, but we're only going to talk about 2 here. are going to be mathematically combined. All right, so again, we sort of have a similar thing in valence bond theory where we combine s and p orbitals to make sp hybrids, but in that case, it's the orbitals on a single atom. In this case, we're going to mathematically combine orbitals from two different atoms, or two or more different atoms if we were going to more complex. So they're going to be mathematically combined. And when we say mathematically combined, we're talking about linear combinations. It's always going to be adding and subtracting, nothing more complex than that. There's always just going to be additive or subtractive combinations of orbitals. And by combining orbitals from two different atoms, we're going to form delocalized molecular orbitals, which don't belong to one atom or another, but actually are delocalized over both of them. And as I said, we're going to talk about one case at the end to start to try to understand this for something more complex than a diatomic, but really we're going to be dealing with diatomic molecules here, just things with two atoms. And when we create these molecular orbitals by mathematically combining the atomic orbitals, we get new orbitals that are delocalized over both atoms. So in order for two orbitals to mathematically combine with each other and form molecular orbitals, there are one major consideration is that they have to be of similar energy. So you're not going to take an orbital that's way up here in energy and an orbital that's way down here and mix them together. They're not going to mix very effectively. So only orbitals that are close in energy can mix together. So we don't have to consider all of the orbitals necessarily, only the ones on the two atoms that are very close to each other. So they have to be close to each other in energy, and really we only care about the valence orbitals. So just like we do for Lewis structures and for the simpler bonding theories that we learned last time, it's really only the valence orbitals that matter. The reason being you have your core orbitals are buried close to the nucleus, they're really low in energy, and they're not going to effectively mix with each other because they're not extending out from the nucleus far enough to actually interact with the other orbitals on the other atom and make combinations. So you only have to care about the valence orbitals. Once again, we don't have to think about all of them. And so that's kind of what we're doing. Now when we do this linear combination of atomic orbitals, we form two types of orbitals. So you take two atomic orbitals from two different atoms and you mix them together in two different ways and you form two different types of orbitals. So you form an additive combination which is called a bonding orbital. So we abbreviate that as psi. It's a wave function. That's a combination of two atomic orbitals. So in a very generic sense, it's going to be one atomic orbital added to the second. Again, these are from two different atoms now to make a delocalized orbital over both of them. So the bonding orbitals are additive combinations. And then the electron density of the bonding orbital, kind of what we talked about last time for sigma and pi bonds, is going to be greater along the bond in between the nucleus. So in other words, we get in-phase combination. We're adding the two together. And so you get an increase in electron density between the two atoms. And we'll see the pictures of that help reinforce that later. So it's greater along the bond between the nuclei. And the energy of a bonding orbital. So we're starting with two atomic orbitals. And if we're starting with two atomic orbitals from two of the same atoms, so let's say it's an oxygen and oxygen or a hydrogen and a hydrogen, those two atomic orbitals that we're mixing, if they're the same orbital, are starting at the same energy as each other. And when they mix together, they form a bonding orbital that's going to be lower in energy than the atomic orbitals. Okay, so anytime you form a bonding orbital, that orbital has an energy level that's lower than the individual atomic orbitals that mix together to make it. Then the other type we have is called antibonding. And so we abbreviate that as psi star. So anytime you see a star next to something, a little asterisk, it means that it's an antibonding orbital. And what that refers to is a situation where we take the same two atomic orbitals, but this time we subtract them from each other. Again, these atomic orbitals are mathematical functions, so they can be added to each other, they can be subtracted to each other, or any other combination of operations. For MO theory, we just add and subtract, as I said. So the subtractive combination is called an antibonding orbital. So it's what we call the out-of-phase combination. So when we do this, the electron density of that orbital, in other words, the region in space where the electron is likely to be if it's in that orbital, that's going to be greater outside the intranuclear region. So it's going to be sort of away from where the bond would be. Okay, so we no longer have electron density reinforced in between the two atoms. It's actually reinforced outside of where those two atoms are. And again, the pictures will make that more clear. And then finally, if we make a bonding orbital that's lower in energy than the atomic orbitals, we're not changing the total energy of the system, so we make an antibonding combination that's higher. Okay, so the antibonding orbital, which is a subtractive combination, is higher in energy than the atomic orbitals. Okay. So that's kind of at a very basic level the mathematics of what we're doing here. We're adding and subtracting orbitals, and we're making new orbitals, one which is lower in energy than the atomic orbitals, one which is higher. All right, but what's going to be helpful for thinking about these types of orbitals is going to be their shapes and their pictures again. So if we do it for 1s, we're going to start with the very simplest system, which is just mixing together two 1s orbitals. If we mix together two orbitals, we get two molecular orbitals, and as we said, one is bonding, one is antibonding. So when we mix 1s orbitals together, just like we saw last time, we're going to classify these types of bonds as either sigma or pi. Now, if we mix s orbitals together, do we get sigma or pi? They start with the same letter, so it's easy to remember. Sigma. Okay, so s orbitals mixed together to give sigma bonds. So we would abbreviate those molecular orbitals with sigma. We put a little subscript that tells us it comes from 1s if we're mixing two 1s orbitals together. That's not 100% necessary, but allows us to understand where that orbital is coming from. And so the sigma orbital formed from two 1s orbitals would just be, again, the additive combination of those two. It's a delocalized orbital, so if we have the two nuclei here and here, our sigma orbital is just a combination of two s orbitals, and we get overlap in between the nuclei. But again, it's no longer two separate orbitals, it's one orbital that we've now formed by combining the two individual atomic orbitals. So a sigma orbital, which is bonding, is going to look like this. And again, we have electron density in between the nuclei. They're the same phase, so they combine in this way. If we do the antibonding, which we abbreviate as sigma star, again, the star tells us that it's antibonding, that's going to be the subtractive combination. And what we get in this case is we have the two nuclei, but what we have is, because they're added out of phase, remember that orbitals have phases, which is essentially the sign of the wave function, so we get one that's positive and one that's negative, and we get a node in between them. All right, a region, again, where the electron has no probability of existing right in between the two. So when we do an out-of-phase combination, again, we get electron density outside where the two nuclei are, and that actually weakens the bond if we start putting electrons into those orbitals, as we'll see. Okay, so this is our antibonding combination. That's what it looks like pictorially. All right, and again, it's not two separate orbitals. It's one orbital delocalized over both atoms. This time it has a node in between the two where it has no probability of existing. Now then, what we do with these, again, the pictures are helpful for understanding. We have limited ability to have you draw pictures in Blackboard, or no ability, so it's not something you're going to necessarily have to do yourselves, but I do think it's helpful to always visualize things when you're trying to learn them. But the more important thing is understanding these orbital diagrams, which are energy level diagrams that show the relative energies of all of the orbitals that you have in a certain molecule. So if we're mixing two 1s orbitals together, we're going to always draw these with energy increasing bottom to top, so low energy at the bottom, high energy at the top. And we're starting with two 1s atomic orbitals that have the same energy if they come from the same type of atom, if it's two hydrogens, for example, that are mixing together. And then, as I said, we get a bonding orbital that's lower in energy than those two and an antibonding that's higher in energy. So in the middle region between the two, we show those new energy levels. So we have a sigma 1s, which is lower in energy. We draw dashed lines to show that the 1s orbitals mix together to make that. And we have a sigma star, which is higher in energy, and again we draw dashed lines to show that those same two orbitals mix together to make the sigma star. Now when we're talking about molecular orbital diagrams, I'm going to draw pretty much all of them today. I'm going to show the atomic orbitals that are used to make them, you don't really necessarily have to think about those for most of the questions we're going to ask you. You just really have to know what order do the two molecular orbitals come in, and as we'll see later on, you then fill those with the correct number of electrons before answering any questions about the properties of that molecule. So we have to know if we're mixing two 1s orbitals together, so if we have just two hydrogen atoms that only have 1s valence orbitals available, we make a sigma 1s, which is lower in energy, and a sigma star 1s, which is higher in energy. This full diagram shows that those come from the atomic 1s orbital. So again, on the outsides of the diagram, we have the atomic orbitals that we're using to mix together and make the molecular orbitals. The center part of this diagram lists just the molecular orbitals in the order they come in once the two atoms come together and make a bond. All right, and one thing we noticed from this diagram is that we started with two atomic orbitals, two different 1s orbitals, and we made two molecular orbitals, and that's always going to be true. So however many orbitals you mix together, we're going to get a little bit more complex than this later today, but the number of atomic orbitals that you combine is going to end up equaling the number of molecular orbitals that you form. All right, so if we mix two orbitals, two atomic orbitals, we make two molecular orbitals. If we end up later on, we're going to mix 8 orbitals together, we'll get 8 molecular orbitals, as complex as we'll go. So that's the situation we have if we have just 1s orbitals mixing together. Relatively simple picture here. All right, so once we have the orbital diagram, as I said, the next thing we're going to do is we're going to populate it with electrons. And as we'll see when we go through all the different combinations and possibilities, we populate the orbitals just like we do for atomic orbitals. We do lowest energy first, we fill up the lower energy orbitals before moving to the higher energy orbitals, and it follows those exact same rules. Now, once we have the electrons arranged into the orbitals, there are a couple of things we can determine from this once we have the correct molecular orbital diagram with the correct number of electrons in it. So one thing is the bond order. We learned bond order is just the number of shared electron pairs. It can be single, double, or triple. And if we draw a Lewis structure, we use octet rules and formal charges to predict whether it's going to be single, double, or triple. But for molecular orbital diagrams, we can also get that information. So the bond order is going to be 1/2 times the number of electrons that are in bonding orbitals. So again, we have combinations of bonding and antibonding orbitals with some amounts of electrons in them, minus the number of antibonding orbitals. And so what this tells us is, antibonding electrons, I should say, not orbitals, but number of electrons that are in those orbitals. So what this tells us is that every time we add 2 electrons to a bonding orbital, we increase the bond order by 1. Every time we add 2 electrons to an antibonding orbital, we weaken the bond order or decrease it by 1. So again, it comes from the combination that are populated, as we'll see. We can also determine bond types. Now, the simple diagram we just did for 1s only has sigma orbitals, because that's all that 1s orbitals can make. But as we'll see later on, you can sometimes have sigma and pi in your diagram. And so knowing which orbitals are populated with electrons, we can predict whether it's sigma, pi, or some combination. So once we know, again, the full orbital diagram and the full number of electrons and how they're arranged, we can predict the bonding type. Now, one thing I will say about all of this is, for bond order, we know how to do that from Lewis structures. For regular, for most things, there's never going to be a disagreement between the bond order you predict from the Lewis structure and the bond order you predict from the molecular orbital diagram. So as we'll see later on, when we do O2, we still predict it's a double bond. When we do N2, we still predict it's a triple bond. So there's never going to be a disagreement there. That said, the molecular orbital diagrams allow us to do odd electron species as well. So if we did a Lewis structure for a species with odd number of electrons, we would have very little idea how to deal with that, and we would get some picture that looks reasonable but is not really accurate. Molecular orbital theory allows us to deal with those very easily, as we'll see. Now, the other thing that molecular orbital theory does is, in some cases, it goes against the prediction of sigma and pi. So we saw also that from the Lewis structure and from valence bond theory, we can predict how many sigma and pi bonds there are. Sometimes that is wrong also, but molecular orbital theory gives us the more accurate picture. So we'll see all that later on. I'm just sort of warning you and prepping you for what's going to come next. Now, we can also predict the magnetic properties. We alluded to this on the first slide as a reason for why we even need this additional bonding theory. So as I said, there's 2 different types of magnetic properties that you can predict. So you have diamagnetic, which means no unpaired electrons. And it's going to be weakly repelled by a magnetic field. I should point out that our book didn't cover this, so we didn't either in class, but we can also do this for atomic configurations. We learned how to figure out how many unpaired electrons there are in an atom based on its ground state configuration, and we can make the same magnetic predictions about those, and we're going to also then apply that today to diatomic molecules. And then paramagnetic is the other type of magnetic property, and that's going to mean you have one or more unpaired electrons. And these would be attracted to a magnetic field. So they behave differently in the presence of a magnetic field, depending on whether there are or are not unpaired electrons. All right, so that's the situation we have. We have two different magnetic properties, and that also we would predict accurately from the molecular orbital diagram, not so much from the Lewis structures. All right, so let's start populating orbitals with electrons. So we started with the very simple diagrams for 1s orbitals. All right, so again, this is just a repeat of what we drew on the previous slide. We start with two 1s orbitals. Here we're doing H2 with a plus charge overall. So we start with two 1s orbitals. Those are the valence orbitals for hydrogen. And we combine to get a lower energy sigma bonding orbital and a higher energy sigma star antibonding orbital. All right, and then what we do is we populate this with the correct number of electrons. So how many electrons does H2 with a positive charge have? 1, because H2 has hydrogen each has 1 electron. There's 2 electrons for H2. We take 1 away for the positive charge. So this has 1 electron. And just like we do for atoms, we fill the orbital's lowest energy to highest energy. So if we have 1 electron, the first electron goes into the sigma 1s, and that's the only electron we have now. Okay? So if we do bond order, remember that we saw how to calculate bond order on the previous slide. It's 1/2. Number of electrons that are in bonding orbitals is what for this one? How many of those electrons? We have 1 electron. Is it in a bonding or an antibonding orbital? It's in a bonding orbital. The lower energy of the one's bonding. So that's 1 electron in a bonding orbital. We have how many electrons in the antibonding orbital? 0. And so what we get is a bond order of 1/2. Okay? So again, we predict a fractional bond order here, which is something that we would never do if we were drawing Lewis structures and using valence bond theory. And so H2 with a positive charge, not a very stable species. You're not going to see that, laying around in the ground. But if it were generated and were studied, it would be found to have a bond order of 1/2, which is just 1 shared electron between the two atoms. Not something we see in valence bond theory. All right, now if we go to go to just neutral hydrogen H2, this has now 2 electrons. Each hydrogen has 1. Same diagram, 1s orbitals from hydrogen mixing to make sigma and sigma star. And now we have 2 electrons to put in, and still following the rules, the Aufbau principle and Hund's rules and Pauli exclusion, all that stuff. If we have 2 electrons, we fill them into the lower energy orbital first. So just like atomic orbitals, molecular orbitals can have a maximum of 2 electrons in them. And when they do, they have one that's spin up and one that's spin down. So that's all the same for molecular orbitals as it was for atomic orbitals. But again, we have to put both of them in the sigma 1s because there are now 2 electrons, and we fill this one first before we would start putting electrons into sigma star. So this configuration would be written as sigma 1s2. We could write the configuration 2 the same way we do for atoms. This is sigma 1s1. This is sigma 1s2. Again, orbital name or subshell in the case of atoms, and then number of electrons. So sigma 1s2 configuration, and the bond order for this guy. Now we have 2 electrons in the bonding orbital, 2 electrons, and both of them are in the bonding orbital. Still 0 in our antibonding orbital, and so we get a bond order of 1, and we would easily predict from other things that we learned that H2 has a single bond, and so this is not at odds with that. But again, we add 1 more electron to the bonding orbital, so we increase the bond order and make it a stronger bond. So we would expect H2, which has a bond order of 1, to have a stronger bond than H2 plus, which has a bond order of 1/2. Again, the larger the bond order, the stronger the bond. All right, so that's what we get for H2 and H2 plus. We can continue on and just be a little bit repetitive here. So now we have H2 minus, or this would be the same diagram that we would get for He2 with a positive charge. So for either of these 2 species here, either of these 2 ions, we predict 3 electrons. H2 with a minus charge is 1 more electron after that, so that's 3, or H2 plus would be 4 electrons minus 1, which is also 3. So either of these would have this same type of diagram. Two 1s orbitals, sigma, sigma star. And in this case, the only difference is now we have a total of 3 electrons to put in, so we go 1, 2, and we have no choice but to put a third one up there. Again, only 2 electrons maximum per orbital, so once we add a third one, it has to go into the antibonding orbital. So when we calculate the bond order for this, what we now have is a total of 3 electrons. 2 of them are in the bonding orbital down here. We have to subtract from that the 1 electron that's in the antibonding orbital. So the sum of these two numbers will always be the total number of electrons. How many are bonding, how many are antibonding. We subtract the 2 to get bond order, multiply by a half, and we get another case where the bond order is exactly 1/2. All right? So by putting one more electron into an antibonding orbital, we weaken the bond. Okay? We saw that in the previous example. Both electrons were in the bonding orbital. That was a bond order of 1. If we add an electron to the antibonding orbital, that causes the bond to get weaker, and that's true anytime we add electrons to antibonding orbitals. Okay? So that's, and then finally, let's do He2. Now, based on what we know about chemistry so far, about a quarter of the way through our Chem 1331 experience, do we expect helium to be able to form a bond with another helium atom? No, because they're noble gases. We said that noble gases don't typically form chemical bonds. They both have 2s2 configurations. They don't want to share their electrons. So let's see what happens if we try to draw a molecular orbital diagram for He2. 4 electrons now to put into this diagram. Still the same diagram because it's still 1s valence orbitals, sigma and sigma star. But if we put 4 electrons into this diagram, we go 1, 2, 3, 4. We fill the bonding and the antibonding orbitals. And without even really thinking about that, we can say, well, if we have a filled bonding orbital and a filled antibonding orbital, those basically cancel each other out and don't have a bond at all. We can verify that by calculating the bond order. 2 electrons in the bonding orbital, 2 more in the antibonding. 2 minus 2 is 0, so we get a bond order of 0. Now, anytime you calculate a bond order of 0, the conclusion then is that the molecule is what we'd say is unstable, or a simpler way to say that is that it does not exist. All right, so any molecule, any diatomic molecule, which is all we're going to do, if you predict a bond order of 0, your conclusion is that that molecule doesn't exist at all. When you try to form a bond between those two, you fill both the bonding and the antibonding orbitals. You cancel that bonding interaction out, and they fall apart. They don't have a bond between them. Okay, so that is also in line with what we learned before, which is that noble gases like helium don't tend to form bonds with each other. All right, any questions on those simpler diagrams before we up the complexity just a little bit? Yes? No, you can't. Yeah, you can't fix this situation. There's no way around this because it has 4 electrons. You can't change the number of electrons. And if you only have 1s orbitals available, you can't make any other types of orbitals. In more complex molecules, there are ways to fix it by basically either changing the shape of the molecule or changing how they're bonded to each other. But for diatomics, you can't really do anything. You form those sets of molecular orbitals, you fill them up with the correct number of electrons, and if the bond order is 0, you're done. It's just not stable. Anything else? Okay, so let's move on then to p orbitals. So if we go into the p block elements, we started with hydrogen and helium, which are in the s block. Now we're going to the p block. We have s and p valence orbitals. And so what happens when we include these? So just like we can for s orbitals, we can form sigma molecular orbitals from p orbitals as well. We sort of saw that last time in valence bond theory, how 2 p orbitals can overlap head-to-head and form a sigma bond. And you can likewise form delocalized sigma orbitals from p orbitals. So we're going to assume here, this is not the standard way to do it, but this is the way our book does it. Assume that the bond axis is in the x direction. All right, so in other words, we have a bond between 2 atoms, and that direction between the 2 atoms is x. And so if we take 2 px orbitals and combine them, we get a sigma bonding orbital. So again, additive combination or in-phase combination gives us a sigma bonding orbital, and we can use p orbitals as well to do that. So we take 1 px orbital. Again, these p orbitals now have figure 8s. Another px orbital where the 2 like phases are lined up with each other. We'll put the nuclei in red so you can see them. They're in the center of these orbitals again. And when we add these together, we get a bonding sigma orbital that now looks like this. It's a little bit more complicated, where we have reinforcement in between the nuclei, but we also have these little regions outside that are the opposite phase. Again, because this is derived from a p orbital, you have the two phases that are alike and pointing to each other add up, and they combine linearly in an additive fashion. These two opposite phases are still there. So the original node that was present in the atomic p orbital is preserved in the molecular orbital, but you still have sigma electron density in between the two nuclei, so this would be called a sigma, so two px orbitals. Let's do some blue. Px, another px, and you get a sigma p type orbital. 2p or 3p, whatever p orbitals you're using, can form this. And then similarly, if we always have bonding combinations, we also have antibonding. You can't have one without the other. So if we do sigma star p, that'd be the subtractive combination. And then what we're doing here is we're taking these same two p orbitals and subtracting them. Now the process of subtracting two orbitals is really the same as taking one of the orbitals and flipping it over. So when you subtract two orbitals, you take one orbital and flip it. So in other words, what we're doing is we're going to put the lobe that's labeled in blue here on top of the lobe that's labeled in white and combine those. So you get what's called a destructive combination or a subtractive combination out of phase. And so what you end up with is an orbital that looks like this. You have your two nuclei, and because we're adding them out of phase, in between the two you have the opposite phases with, again, a node between them, and then you have outside the nucleus more electron density of the opposite phase. So it looks sort of like this. Two out of phase p orbitals where we flip this one over, we end up putting the two lobes on top of each other that are out of phase, and that causes them to cancel each other out basically and get an orbital that looks like this. But again, the key point is that this is an antibonding sigma p orbital. I don't think we're going to do too much with orbital pictures in the homework questions and test questions, but I still think visualizing them can be helpful to learn this. All right, so we still get a set of sigma and sigma star with p orbitals. But as we talked about last time, p orbitals can also combine side to side and form pi bonds. And so we also get pi molecular orbitals. So in this situation, if we have two, let's say, py orbitals, so we saw that the x direction was the direction of the bond, sort of the head-to-head overlap to form a sigma. If we go in the y direction and take two py orbitals, which would be facing this way in the orientation that we're using for this introduction. So we have two py orbitals. And again, they can form a delocalized, sorry, I should do this in red. Red, nucleus there, nucleus there. They can form a delocalized orbital that has electron density above and below the bond axis, a pi type orbital. All right, so again, it's one orbital that forms from these two things combined, and you get sort of this type of shape where it's overlap above and below the nucleus in phase again. So this is your pi p orbital. And if you get pi bonding orbitals, you also get pi antibonding orbitals. So anytime you have the bonding combination, you also have the subtractive or antibonding. So the pi star from the p orbitals is going to be the two subtracted from each other. So you take these two orbitals and subtract them. And again, the process of subtracting two orbitals is the same thing as flipping one of them over and trying to add them that way. So when we flip one of these over, we have this sort of situation. So this one is arranged in the same orientation, but this one we flip the orientation, so now we have unlike phases that are lined up with each other above and below. So they don't form a constructive overlap. They instead form this with, once again, a node in between the two. And this is your pi star combination. All right, so again, no reinforcement in between the two atoms. You just have electron density outside the region where the two would be bonded to each other. So bonding and antibonding combinations. And then the same thing happens. I'm not going to draw them out again. But we also have the pz orbital. So the pz orbital, which in this orientation will be coming out of the board towards you, so not easy for me to draw, those also would overlap side to side to form pi and pi star. So that those combinations also exist. And so when you form pi orbitals using p orbitals as the atomic orbital basis, what you get are really two sets of pi and pi star orbitals, and those are each at the same energy as each other. So you get two pi orbitals at the same energy, one in the y direction, one in the z, and you get two pi star orbitals at the same energy, one in the y direction, one in the z. So they're just rotated, but they're the same energy. So here we have degenerate orbitals that form. So we give two degenerate pi p and pi star p orbitals. And we'll see this on the diagrams that we're going to draw here in a second, but it's not that all four of these are at the same energy. You still get the bonding orbitals lower, antibonding orbitals higher, but the two bonding orbitals are at the same energy as each other, and the two antibonding orbitals are at the same energy as each other. So it's two sets of degenerate orbitals, bonding and antibonding. So that's the difference with p. We have two different ways of combining them. So then when we look at the diagrams, I'm not going to draw this one by hand because it gets more complicated. Here's the picture that results. So if we're going to do the p block elements, we're going to do O2, F2, and neon 2. We're going to start with these ones because there are some slight differences with the other p block elements that come earlier, and this one I think is the more intuitive ordering of the orbitals. So let's see what we have. For oxygen and nitrogen, fluorine, and so on, we have 2s and 2p valence orbitals. So again, the outside of our diagram is going to be the valence orbitals. No, I wrote that wrong. I got ahead of myself. Those are just 2s and 2p atomic orbitals. All right, so again, the outside of the diagram is for the individual atoms to the two oxygens in this case that we're bringing together, and then they combine to form molecular orbitals, which are shown in the center of the diagram. So just like before, when the two s orbitals combine, they form a sigma and a sigma star. That's all the s orbitals can form, a sigma and sigma star. And then when the two p orbitals combine, we just saw that they can form sigma and pi. So there's two different ways of combining the p orbitals. And so what you get, which one of these are higher and lower in energy than each other? So one thing we haven't talked about yet, but is another important principle in molecular orbital theory, is that when two orbitals combine with each other, how strongly they overlap with each other is going to determine how low the bonding orbital goes and how high the antibonding orbital goes. So if we have a sigma bond, which is two head-to-head orbitals coming with really strong overlap, that energy spacing is going to be greater. So when the two p orbitals, the px orbitals, combine to form sigma bonds, that bonding orbital is going to be the lowest. It's going to be lower in energy than the atomic orbitals because it's a bonding orbital and it's a really strong overlap, so it goes down even further. Whereas the pi bonding orbital, it's still going to be lower in energy than the atomic orbitals, but not by as much, because for pi orbitals we have side-to-side overlap, which is not as strong of an overlap, so you don't get as much energy stabilization when you form that type of interaction. Same thing for the antibonding orbitals. The antibonding orbitals are higher in energy. The sigma star is going to be way up here because, again, a strong head-to-head sigma overlap results in a large destabilization of the antibonding orbital, and then the pi star is going to be still higher in energy but not by as much because it's a weaker overlap, so your antibonding orbital doesn't split as much. So this is the diagram we get. We'll use the same exact diagram for oxygen, fluorine, and neon, those P4, P5, and P6 electron configurations for the atoms. And how many do we have to put in for O2? So how many valence electrons does oxygen have, diatomic oxygen? 6 each, so a total of 12, right? Because it's two oxygens, each with 6 valence electrons, or group 6. So all we have to do then is put 12 electrons into this set of atomic or molecular orbitals. All right? So we just go from lowest energy to highest energy. We have to put 12 in, so we get 2, 4, 6, and then we do, again, following Hund's rule, 7, 8, 9, 10. And then when we get up here to the pi star 2p, we have 2 more to put in, and we have to unpair them just like we would for atomic orbitals. So 11, 12. The labels always get in the way, so let me put that label off to the side. And what we end up with is in this highest orbital here, we get 2 unpaired electrons because, again, they're 2 degenerate orbitals, so we fill them one at a time with the same spin before we pair them up, just like we did for atomic orbitals. All right? And so there's some important features here that I want to point out. So these 2 unpaired electrons allow us to predict that O2 is paramagnetic. Again, we saw that experimentally in that video that I showed, and the molecular orbital diagram gives that prediction out that it's paramagnetic. So this bonding theory matches the experimental observation much better. So this is an example of the scientific method in action. You have a bunch of observations, you try to explain them with a theory, and if your theory breaks down somewhere, you have to make a more advanced and better theory, and that's exactly what we did with molecular orbital theory. So it builds off of valence bond theory and allows us to make predictions that would not be possible with that simpler bonding theory. And then if we calculate the bond order, it's still the same formula, 1/2, but now we have a lot more electrons to deal with. So 12 total electrons. We have to figure out how many of those 12 are in bonding orbitals. Remember that bonding orbitals are the ones that don't have stars next to them. So we have these two that are in a bonding orbital, 4, 6, 8. So 8 of our 12 electrons are in bonding orbitals. We have 2 from the 2s, 2 from the sigma 2p, 4 from the pi 2p. So a total of 8 that are bonding, and then the rest of the 12, which should be 4, will be antibonding. So we have these 2 electrons here that are in the sigma star 2s antibonding orbital, 2 more electrons in the pi star, so a total of 4 antibonding electrons, 8 minus 4. So we predict a bond order of 2, which is exactly what we drew. So there's the bond order predicted from the Lewis structure and from the MO diagram are not at odds with each other. We'd also predict that the bonding is 1 sigma and 1 pi. These 2 sigma and sigma star cancel each other out, but then over here we have a filled sigma 2p, which is not canceled out by the sigma star, so we have 1 net sigma bond. We have 2 pi bonds, but they're going to be canceled out by pi star. One of them is going to be canceled out, so that leaves us with 1 sigma and 1 pi as our net bonds in this molecule. Again, same as what we would predict from valence bond theory. And if we write out the electron configuration, we again go just like we do for atomic orbitals, start with the lowest energy, sigma 2s, that has 2 electrons. Sigma star 2s has 2 electrons. We have the sigma 2p, which also has 2 electrons. We have pi 2p, which has 4 electrons. Remember, the pi orbitals can hold up to 4 electrons because there's 2 of them. And then we have pi star 2p, which has 2 electrons. So we can write out electron configurations also from molecular orbital diagrams that look a lot like atomic configurations, but they use these sigma, sigma star, pi, pi star abbreviations for the molecular orbitals. Okay? So again, it's really a factor of, for you guys, learning this middle part of the diagram, the order that these orbitals come in, sigma and sigma star from the 2s, sigma, pi, pi star, sigma star. So knowing that order and then putting the correct number of electrons in is really what this boils down to. So any questions on that? All right, we're going to see a little bit of repetition, so we're going to go now to F2. From valence bond theory, we would predict that F2 is a single bond. If you draw that out as a Lewis structure, you'd see that. So let's see if that works also for here. F2 now has 14 electrons because it's 2 fluorines, each are group 7. Okay, so we have 14 electrons to put in here. Same exact orbital diagram. 2s and 2p valence orbitals from each fluorine. And then when they combine to form F2, we get sigma 2s, sigma star 2s. So sigma and sigma star. We get sigma 2p, pi 2p. Those are our bonding orbitals from the 2p's. And then we also have our antibonding pi star, sigma star. So same exact diagram, same exact ordering of the orbitals this time. But this time we have to put 14 electrons in. So we go 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this time we completely fill the pi star 2p, pi star 2p. We predict that this is diamagnetic, which is true experimentally. So F2 is diamagnetic. And then if we do the bond order for this, we said that if we drew the Lewis structure, you would get a single bond. And let's see if we get the same thing here. So we have 14 electrons. We still have 8 of those in bonding orbitals, 2 down here, 2 here, 2 more, 2 more. So a total of 8 bonding electrons, 2, 4, 6, 8. And then the rest of our 14 electrons, 2, 4, 6, are in antibonding orbitals. Those are the ones that have stars next to them. So we get 1/2 times 8 minus 6 is 1. We also predict a single bond, or a bond order of 1 from the MO diagram. And then the configuration for this would be again, write them in order, sigma 2s2, sigma star 2s with 2 electrons, sigma 2p with 2 electrons, pi 2p has 4, and the pi star 2p now also has 4. So that's the electron configuration for the F2. All right, and then finally the last one we'll do from this block of elements is neon 2. Now just like we saw for helium 2, we would predict that neon is not going to form a bond with itself because it's a noble gas. So intuitively we don't think this is going to work, but let's see what happens if we try to do it. So now we have to put 16 valence electrons into this diagram. 8 from each neon is a total of 16. And then we label these exactly the same way. As I said, you don't have to necessarily put the outer part of this diagram, the atomic orbitals, in. This just shows us where the molecular orbitals come from, so it's helpful to look at. So we get sigma 2s and sigma star. It's really, again, only the center energy levels that matter for us when we're solving these types of questions. Sigma 2p and pi 2p, and then pi star sigma star. All right, so this is our orbital diagram. Now we have to put 16 electrons in for neon 2 and E2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we've again filled our entire diagram. Just from that, we would predict that all of the bonding interactions cancel out because the same bonding orbitals are also filled. So we have sigma and sigma star from the 2s, pi and pi star from the 2p all filled, sigma and sigma star from the 2p, pi and pi star from the 2p. All of those are all filled with, so we expect all the bonds to cancel each other out and not actually have a real bond. And if we predict the bond order from this guy, we have 16 total electrons, 2, 4, 6, 8 of them are still in bonding orbitals. You're never going to have more than 8 electrons in your bonding orbital because we only have 4 bonding orbitals in these diagrams. But now we also have 8 electrons in antibonding, 2, 4, 6, 8. So we again predict a bond order of 0. So this would be an unstable molecule, one that doesn't actually exist. So it doesn't do any good to write an electron configuration for a molecule that doesn't exist or to predict magnetic properties for a molecule that doesn't exist. It's just we predict from the MO diagram that it's unstable, has a bond order of 0. All right, so those are one type of MO diagram. Again, it works for the second half of the P block, oxygen, fluorine, neon, P4, P5, P6. If we go to the first half of the P block, it's very similar, but as I'll show you, there's one key difference. So this is going to be the diagram we have if we were making diatomic molecules from boron, carbon, nitrogen. This will be, again, P1, P2, and P3, the first half of the P block. So let's look at what this one looks like. It's still the same valence orbitals here. Okay, so still the same valence orbitals. We have 2s and 2p. These are still P block elements, so we're not going to use anything different in terms of valence orbitals. We again can write the atomic orbitals on the outside, the molecular orbitals in the middle. We're doing B2 first. So what we get in this case is still sigma and sigma star for the 2s's, so those don't change. But then when we go up to the 2p level, something happens. And what we notice here is that our degenerate pi 2p orbitals now come first. Normally it's in the other ones it was the sigma that came first, now it's pi. And then we get still pi star and sigma star, so those don't change. So the only difference in this diagram is that these orbitals here switch their order. So if we're talking about B2, C2, and N2, again, the first half of the P block, P1 through P3, these two orbitals are now in a different order than they were for the other ones. That's the only difference you have to remember between them. Everything else is the same. Now, the reason for that is kind of complicated, but essentially what it boils down to is that, as we see, we have sigma orbitals from the 2s and sigma orbitals from the 2p, and it's possible for those to actually mix with each other. So because they're both sigma, it's not simple as just two s orbitals and two p orbitals mixing together. You actually get s and p all mixing together in more complicated combinations. And why it happens here is that for the first half of the P block, the s and p orbitals are closer in energy to each other, and so they're more energetically aligned and able to mix together better. So it's, again, something that we don't have to worry about the reason, but if you're curious why that is, it's because we have what's called sp mixing, where we no longer have pure s and pure p orbitals in the sigma. We actually have a combination that's s and p together, and so you get a more complicated situation. That changes the order of these two orbitals is really the result that you have to worry about. So changing the order of these two orbitals, it's not so important if you're just predicting the bond order. You'll get the same bond order whether you do that or not, because we're just switching the order of two bonding orbitals. However, if you want to predict the number of unpaired electrons correctly, you do have to make sure that this order is correct, the pi and the sigma for the two p's. Okay, so you have to make sure you use the correct ordering if you're going to predict unpaired electrons correctly. So that's going to be the case that we want to keep in mind as being different. All right, so when we fill it for B2, boron has 3 valence electrons, so B2 has 6 valence electrons, and now we add them into this diagram. 3, 4, 5, 6. So we would predict that B2 is paramagnetic. We have 2 unpaired electrons in the pi 2p orbitals. Our bond order for this is going to be, we have 6 total electrons. We have 2 down here that are in a bonding orbital, 2 more up here in a bonding orbital. So 4 out of our 6 are bonding. The other 2, which are sigma star 2s, are antibonding. So we predict a bond order of 1 with a configuration of sigma 2s 2, sigma star 2s 2, and then pi 2p is going to also have 2. So 2 electrons in each of these 3 orbital levels. But the weird thing about this diagram that we would never predict from valence bond theory is that this is a bond order of 1, it's a single bond. In valence bond theory, we would automatically say, oh, bond order of 1, it's a sigma bond, done. But what we see here is that we actually have a pi bond, because this sigma and sigma star cancel each other out. What we're left with in net is a pi bond. So even though it's a single bond, we predict that it's a pi. So again, that's another weird outcome that comes from molecular orbital theory that you wouldn't predict from valence bond theory. A situation where it's a bond order of 1, but it's a pi bond and not a sigma bond. All right, any questions on why that is or anything else about this diagram? All right, so that's diboron, B2. If we go on to C2 and N2, we use the same diagram. So C2 is going to be now 8 valence electrons, and it's the same exact ordering, 2s and 2p atomic orbitals from carbon combined to make dicarbon C2, not a stable molecule, but one that we could potentially study over short time scales. And the 2 s's combine to form a sigma and a sigma star. And then the 2 p's combine to form pi and sigma, but again, in these elements, the pi comes first at the bonding level, and then sigma. Antibonding stays in the same order, pi star, then sigma star. All right, so that's the diagram again for C2, 8 electrons, so we go 1, 2, 3, 4, 5, 6, 7, 8. So that's the diagram for dicarbon. We predict that it's diamagnetic. None of the electrons are unpaired, and that is indeed true experimentally. The configuration is sigma 2s2, sigma star 2s2. And then we have pi 2p now has 4 electrons, so 2 more electrons still going into the pi 2p level. We fill lowest to highest as always. The bond order for this, we now have 6 electrons in bonding orbital, sigma 2s2, pi 2p4, a total of 6 that are bonding. These 2 that are still antibonding from the sigma star, and what we end up with is a bond order of 2. So we predict a double bond in this case, but again, it's a weird situation that we wouldn't predict from valence bond theory. So from valence bond theory, we would say a double bond is 1 sigma and 1 pi, but if we look at this diagram, the sigma 2s cancels out with the sigma star. All of our net bonding electrons are in pi orbitals, so we now have 2 pi bonds. So no sigma bonds, but 2 pi for our double bond. Again, something that we would not get from valence bond theory. So when you're predicting the bonding in diatomic molecules, typically we're going to have you do it this way. You're going to draw the molecular orbital diagram and look at whether the net bond falls in a sigma or a pi level, depending on how many electrons you have and which orbitals are filled. And again, this is a situation where we do predict a double bond that's 2 pi bonds as opposed to 1 sigma and 1 pi, which is conventionally how we think about it in the simpler theory. All right? And then the last one we'll do for neutral elements is nitrogen, N2. We've probably drawn the Lewis structure of this before. It's a triple bond, and we would predict diamagnetic from the Lewis structure as well. So now we have 10 electrons to put in this diagram. 2 nitrogens, 5 electrons each. Same valence orbitals, so a lot of repetition here. To just draw the diagram, nitrogen, nitrogen, and 2 orbitals, molecular orbitals in the middle. And we get sigma and sigma star. Pi 2p first, sigma 2p next. Again, that's the order that changes in these earlier p block elements. Pi star, sigma star. All right, same orbital diagram as the last ones. This one, if we actually got the order wrong for neutral dinitrogen, we would make the same predictions, but it still is useful to have it in the correct order. And so we have 10 electrons. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've completely filled all of the bonding 2p orbitals. We predict it's diamagnetic. Remember from the video, they didn't do a very close-up of it, but when they poured nitrogen through the magnets, those went right through. So nitrogen is in fact diamagnetic, and that's what the prediction from the orbital diagram is. The bond order for nitrogen, we said, should be a triple bond based on its Lewis structure. And when we calculate it, what we see is we have 2 from the sigma, and then 6 more up here. So 2, 4, 6, a total of 8 bonding electrons. The most that we can have in any diatomic molecule is 8. We have 10 total electrons, and only 2 of them, the sigma star electrons from the 2s, are going to be antibonding. So it's 8 minus 2 times a half. Bond order of 3. We do predict it's a triple bond. We also predict it's 1 sigma and 2 pi, just as we would for valence bond theory. So nothing weird about this orbital diagram that we wouldn't predict from the Lewis structure in valence bond theory. All right, electron configuration would be sigma 2s 2, sigma star 2s 2, pi 2p4, sigma 2p 2, and triple bond, at least in the ground state, a triple bond is the highest bond order you can get from this type of diagram. You can't get anything higher than a triple bond. Try to convince yourself that's true, because you're always going to fill this sigma star before you fill these bonding levels. So you're going to maximize at a bond order of 3, which is exactly what we have here. Yes?
Why not putting the electrons on the sides?
I could do that. So I was just, I guess, being lazy if you want to be blunt. But essentially the side of the diagram just shows the individual atoms. So if we were doing that for nitrogen, that's actually a good point. We could do it. You would show that each nitrogen atom is 2s2, 2p3. So the individual atoms start like this. And then when you combine them, they form molecular orbitals that have that arrangement. So you could put it in. It's not that you don't have to or shouldn't. It's just that it doesn't really give us any additional information beyond what we already know about the atomic configuration. But yeah, it could certainly be there, you're right. So that's what it would look like. You just use the atomic configuration on the outsides, which shows the individual atoms and what they look like before they mix together to form these molecular orbital levels. Okay, any other questions? Yeah.
So do all P1 elements switch the sigma and pi?
They switch the sigma and pi when it's the first half of the p block. So boron, carbon, nitrogen, which are the first 3 elements in the p block, or that whole column, all those columns basically, those first 3 columns. The second 3, which is group 6, group 7, group 8, the oxygen, fluorine, and neon columns, although neon doesn't really matter, those would use the more conventional ordering where sigma comes first, then pi. So it's those energy levels that sometimes switch, and it depends on which element is involved. Now, we will give you some on the homework assignments and tests where it's 2 different atoms bonded together, like let's say nitrogen and oxygen. And in that case, we would specify what order to put them. We don't expect you to know all of the combinations. But for the homonuclear molecules that have 2 of the same atom, that's the order that you need to be able to recognize for the 2 possibilities. Okay? Anything else? Yeah. We're not going to do anything with transition metals, no. So if you guys want to learn about transition metals, you can take 2 inorganic chemistry courses, and then you can take my advanced inorganic chemistry course, and you'll have all that covered. But that's a little bit later for most of you guys. All right. Or maybe never. All right, but hopefully some of you will. All right, so now we're going to do one more. Again, we saw in the cases of, H2 plus and He2 minus, or H2 minus, they can get fractional bond orders. We can also get fractional bond orders if we have, again, either 2 different elements that give us an odd number of electrons, or an ion in this case, like N2 plus. So if we do N2 plus, N2 has 10 electrons, so this would have 9. 2s and 2p. Because it's still nitrogen, we still would predict that the ordering is the same. Just because it's a positive charge, that doesn't change the ordering at all, unless we're told otherwise. Now this one it'd be a little bit weird to put the atomic orbitals in, but we could do that. So if we're making N2 plus, we could think of that as being a combination of nitrogen, so still 2s2, 2p3 if we want to fill in this side of the diagram, with nitrogen plus to make N2 plus. That's one formalism for how we can make N2 plus. So N plus would only have 2s2, 2p2, it'd have one fewer electrons. But again, the outside of the diagram not important for us. What we need to be able to do is put the correct number of electrons into the center part, which is our molecular orbitals. We have 9 electrons, we still follow the same order. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So we do leave one unpaired electron. If it's an odd number of electrons, there's going to be at least one that's unpaired. I guess exactly one in most cases, in every case that I can think of. One unpaired electron, paired magnetic. If it's odd numbers, that has to be the case. So the configuration for this would just be, as soon as it lets me write it, all right, sigma 2s2, sigma star 2s2, pi 2p4. We've just taken out one of the sigma 2p electrons, make it sigma 2p1. So again, if we want to get the accurate configuration, we need to have these two orbitals in the correct order, or else we would have predicted, in this case, that we would have a partially filled pi instead of a partially filled sigma. So that's the correct configuration. If we do the bond order, we now have an odd number of electrons. So when we do this, we get 7 that are bonding, these 2, 4, 6, and then that one odd electron is still bonding. So that's a total of 7. The other 2 of the 9 are going to be anti-bonding, still in the sigma star 2s. And so what we predict, again, is a fractional bond order of 2.5, in between a double and a single. So stronger than a double, weaker than a triple, in between a double and a triple. Can't talk today. So it's a 2.5 bond order, intermediate between double and triple bond in terms of strength. All right, so fractional bond order, again, that we can predict if we have odd numbers of electrons. No easy way to indicate that or draw that if we were doing Lewis structures and valence bond theory. All right, so any questions on those diatomic MO diagrams before I move on to the very last topic we're going to cover in this chapter? Yes?
Why is it on the top if you put the pi and sigma and you put the pi and sigma again?
It's, so one of them is bonding. So these are the bonding combinations, which is the in-phase additive combination that's lower in energy than the atomic orbitals. And these are the antibondings. They have a little asterisk next to them to tell you that they're antibonding. So in the p orbital levels, we're mixing together 6 total orbitals. 3 p orbitals from here, 3 p orbitals from here. So we will get 6 molecular orbitals. 3 that are bonding, 2 pi's and a sigma. 3 that are antibonding, 2 pi's and a sigma, with a star next to them to tell us that it's antibonding. So anytime you mix together atomic orbitals, you get bonding and antibonding combinations. You can't have one without the other. Okay? Yep. Because 7 minus 2 is 5, and half of that is 2.5. No, so that's mathematically why. Now the reason also is because you can't go beyond a bond order of 3. So if you want to actually compare it to the last diagram, this actually brings up a very good point, so I don't want to be too dismissive of that question. So this diagram here, we saw there's a triple bond order of 3. If we remove an electron from a bonding orbital, the bond has to get weaker. So remember, the less electrons you have in bonding orbitals, the lower the bond order should be. So by removing one electron, we decrease the bond order by 1/2. So you get a 2.5 bond instead of a 3.5. You can't go beyond 3 in these diatomics anyway, but removing electrons from bonding orbitals weakens the bond, or adding electrons to antibonding orbitals. So if we went to N2 minus instead, if we added one more electron from this diagram up to here, that would also cause the bond order to go to 2.5, but in a different way. Okay, so that actually is a good point to emphasize that's related to these diagrams. Anything else? All right, I do want to cover this last topic. And so one thing that your book goes through, which is, it's kind of advanced, but I think it's kind of cool also, and we're not going to ask you really many detailed questions about this, is delocalization in more complex molecules. So we're not going to really go through the rigorous details of the molecular orbital diagrams, but we can see a little bit how this works, and what exactly does it mean to have these delocalized orbitals in larger molecules. So we're going to consider the organic molecule benzene, C6H6, pretty carcinogenic, so not something you want to be drinking or breathing in. Anyway, it's, what it looks like is this. So we're going to draw, it's a ring of 6 carbon atoms. So this next few slides is going to really test my mediocre artistic abilities, because I have to draw it gets even worse in the next slide, but this one's pretty easy to draw. So benzene is a ring of 6 carbon atoms. Each of them has a bond to a hydrogen outside of the ring. And then what we have to complete the octets of all of these is going to be alternating single and double bonds. So we can draw one like this, where we have, again, double, single, double, single, double, single, as we go around, alternating single and double. Now what you might recognize is that there's actually 2 ways of drawing this. So we have resonance forms. Okay, so this double bond we could actually have over here instead, and we can alternate the other ones as single and double. So there are 2 equivalent resonance forms for this molecule that still have the same ring of 6 carbon atoms. Should be a perfect hexagon, but I'm not going to come close to drawing a perfect hexagon in any of these, so just beware. It is a regular hexagon, all same bonds and angles. And so this time we just alternate. We start the first double bond here and alternate them like that. So we just switch the positions of the double bonds. Again, whenever that's possible, we have what's called resonance. All right, so we have 2 resonance forms. We sometimes draw this as in this way to indicate that. So we have our ring of carbons. And sometimes to indicate that we have this delocalized pi electron, so these pi electrons that can be in multiple positions, we just draw a circle in between them to indicate that we have pi bonds that are delocalized over the whole ring. That's just a way of drawing it. We'll see more details about how the orbitals look here in a second. So the key feature is that all of these carbon-carbon bonds, which are in between single and double, they're 1.5 bond order because they alternate between single and double. So all CC bonds are equal in length. So I'm drawing that as a single bond with a dash bond because it's 1.5. But that's the key point is that they're all equal length. And then thinking back to last time, if we were to use valence bond theory, what will we predict is the hybridization of all of these carbon atoms? How many electron groups do they have? It's either 2, 3, or 4. So each carbon is attached to how many things? Well, it's attached to 3 things. It has 4 bonds, of course, but 2 carbons and a hydrogen for each one. We don't count double bonds as individual electron groups. Remember, it's just the number of electron groups. So this carbon has a total of 3 things bonded to it. So that's going to give sp2 hybridization. So from valence bond theory, we would predict sp2 hybridization. And we can model then the sigma bonds using valence bond theory. So this is where my artistic abilities are going to really get tested. So if we have each carbon is sp2 hybridized, remember that it's going to have a set of 3 sp2 orbitals, and those sp2 orbitals are going to be arranged into a trigonal planar arrangement, 3 electron groups, okay? So you have an sp2 orbital that goes out like this, like that, and like that for the first carbon. And then the second carbon over here, we're going to have an overlapped sp2 orbital that forms a sigma bond. And then that's going to be arranged like this. That should be more vertical. Let me fix that a little bit. So we have another sp2 carbon there. Not yet. Carbon down here. Overlapping orbital. So basically what I'm drawing on each of these carbon atoms is a set of 3 sp2 orbitals that are going to overlap with the carbon next to them to form a sigma bond. So from a valence bond standpoint, we can model the sigma bonding in all of these. So you have another carbon here with overlaps to that one. I hope this works out okay because it's getting dicey. Carbon. That's big. That's too small, that's too big. Let's do that a little bit better. A carbon with 3 sp2 orbitals. Another, that's too big. As you guys see, I'm getting nervous now. And carbon there. This one's going to have to be a little bit long. Carbon there, carbon there. I can probably move that a little bit and fix it. Try it that there, and there. So pretty bad, but a ring of 6 carbon atoms with all sp3 orbitals all overlapping around the ring to make sigma bonds. Yes? Yes, good point. Carbon there, carbon there, carbon there, carbon there, carbon there. So I think there is a picture in your book of this, so you can see it better than I can draw it probably. But again, it's 6 carbon atoms in a hexagon. Each one of them has 3 sp2 orbitals that come off in a sort of triangular arrangement. And then on the outside, we have the 1s orbitals from hydrogen that overlap with that. All right, so we have CH bonds on the outside where that last orbital that's facing out from the ring is going to overlap with hydrogen 1s orbitals. So we have hydrogen 1s overlapping on the outside. So these are the sigma bonds in benzene. Not the most important part, but it shows that we can use valence bond theory, sp2 hybridization, to form a ring of 6 atoms with sigma bonds between each of the neighboring carbons, as well as sigma bonds to the hydrogens on the outside. Now, then we can go and talk about the pi bonding. So we're going to use delocalized molecular orbitals to describe the pi bonds. So if we draw this hexagon of carbon atoms and look at sort of a side view of it, so a little bit tilted to show a side view of this. So remember that each of these carbons is sp2 hybridized. So it's carbon, 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 carbon. And if you have 3 sp2 orbitals that are in the plane of the ring, what else do you also have on these carbon atoms? Are there any other orbitals on the carbon? All right. Let's think about it. Think about it. Okay, so remember that the sp2 orbitals are going to take one of the s orbitals and 2 of the p orbitals and hybridize them. That still leaves one more p orbital that's unhybridized. And those p orbitals are going to be located perpendicular to the plane of that ring of carbon atoms, to the sigma bonds. Okay? So you're going to have a p orbital on this carbon, a p orbital on that carbon, a p orbital there, p orbital there. All of these are perpendicular to the ring. Okay? So you have p orbitals all the way around. They have their opposite phases. And so then what you end up getting, and what molecular orbital theory then predicts for us, is that you have delocalized orbitals that form from combinations of all 6 of these p orbitals. So when one of those combinations, they all line up in phase, and they form this pi bond that's not just delocalized between 2 atoms, but delocalized over all 6, and forms a ring of electron density above and below the plane of that. And that's exactly what this picture is showing here. So your pi orbital is delocalized now over all 6. In reality, there's going to be 6 pi orbitals because there's 6 p orbitals to combine, but one of them has complete delocalization over all of them. It's more complicated to show all the rest, but essentially the picture that evolves is that we have delocalized pi molecular orbitals, and they're going to be formed by overlap of 2p orbitals in the z direction, where xy is the plane of the molecule. All right, so again, this just is one example to highlight the concept that when we have molecular orbital theory, we're not just forming interactions between 2 adjacent atoms and they're having their orbitals overlap. We have, in many cases, orbitals that are delocalized over the entire molecule over much longer ranges, and that, as we'll learn later on, can be a little bit predictive of some of the key properties, and this will be a key point you see all the time if you take organic chemistry. All right, that takes us to the end of today. Next week, we're going to jump into Chapter 5, so you should be ready now to do the homework in Chapter 4, which will be due on Sunday. Having a little issues here stopping the video.